Welcome to this explainer. Today we're diving into what is basically a massive high-stakes cosmic detective story. We're going to figure out exactly how scientists can look at just a tiny, slow-moving speck of light in the dark and somehow calculate an asteroid's entire trajectory. It's honestly absolutely fascinating. Picture this. You're looking up at the starry night sky. All of a sudden, you spot this luminous little dot. But unlike the stars around it, this thing is actually moving. The very first question that pops into your head, the one that immediately demands an answer, is pretty simple. Where exactly is it going? And once you start watching that dot, your next thought is naturally going to be about its long-term path. Because these objects orbit the sun just like we do, they follow very specific mathematical routes. So you kind of have to wonder, is this path going to bring it back around like a boomerang? Is it hanging out safely in the main belt between Mars and Jupiter? Or is it on a much wilder ride? Which leads us right to the absolute most critical question. If this moving dot happens to be a near-Earth object, an asteroid whose orbit crosses our own, does it pose any imminent danger to our home planet? Answering this definitively isn't just science, it's literally a matter of global safety. Section 1, the mystery in the sky. Section 2, the science of astrometry. Okay, so to answer all of these critical questions, we actually have to start with a really fundamental problem. When a brand new asteroid is discovered, literally nobody knows its complete orbit around the sun. All we have are a few faint dots captured over a couple of hours. The full path? Totally unknown. The solution to solving this cosmic mystery is astrometry, the science of measuring the exact positions of objects in the sky. It's the tool we use to meticulously track an asteroid's slight movement against the fixed background of distant stars over a single night. Now, to map these movements accurately, astronomers obviously can't just say, it moved a bit to the left. They use a highly precise celestial grid system made up of right ascension, or RA, and declination, or DEC. Think of these exactly like longitude and latitude, but projected outward onto the inside of a giant sphere surrounding the Earth. Every single star, galaxy, and speck of dust has an exact coordinate on this grid, and that allows us to pinpoint an asteroid's location with just staggering accuracy. Section 3, from pixels to positions. But here is where it gets tricky. Our modern telescopes capture these images using digital CCD or CMOS cameras, meaning our initial data is literally just raw pixels on a screen. And a pixel coordinate doesn't tell us where an asteroid actually is out in the solar system. So to translate those pixels into real sky coordinates, we use a brilliant technique called plate solving. It's basically like facial recognition, but for the sky. The software takes the image and matches the unique star patterns in the background against ultra-precise databases, like the European Space Agency's Gaia catalog. Once it finds a match, boom, it calibrates the image and transforms raw pixels into exact celestial coordinates. But there is a massive catch here. Time is unbelievably crucial to this entire process. Some of these near-Earth asteroids are moving incredibly fast. So fast that a clock error of just 1 single second on the telescope's computer can completely ruin the measurement of the asteroid's position. Literally, 1 second. Because of that razor-thin margin for error, observatories don't mess around with standard clocks. They sync their systems using highly precise GPS or network time protocol servers. When you're tracking a massive space rock hurtling toward Earth, you really don't want your computer clock lagging because it didn't sync properly over the Wi-Fi, right? Every single valid measurement absolutely must log 3 things: the exact UTC time down to fractions of a second, the precise celestial position, and the unique code of the observatory taking the picture. Section 4, calculating the exact trajectory. So, once we've collected a bunch of those highly accurate time-stamped coordinates, it's time for the heavy orbital math to take over. At first, predicting the orbit is kind of like trying to guess a car's entire cross-country route when you've only seen it drive down a single street for 2 seconds. It creates what scientists call a cone of uncertainty, this massive spread of possible paths the asteroid could take. But as we gather more and more observations, we feed that new data into the computers, and that cone of uncertainty continuously shrinks, collapsing down until one exact definitive path becomes totally clear. The computers crunch all these observations to find the one single trajectory that best fits the data. The output is a set of parameters called orbital elements. Now, I know things like semi-major axis, eccentricity, and inclination sound like a massive wall of scientific jargon, but it's really just a mathematical way of defining the orbit's physical reality. These numbers simply tell us exactly how squished the orbit shape is, its precise average distance from the sun, and how much it tilts compared to Earth's flat orbit. And it's entirely thanks to these complex orbital calculations that we can definitively predict the future. This math gives us the incredible power to look years or even decades ahead, allowing us to know exactly when an asteroid will approach Earth, exactly what its distance will be, and whether it represents a real calculated threat.
Section 5, Planetary Defense in Practice.
Now, turning all these mathematical calculations into actionable safety measures is no small feat. It requires a massive, globally cooperative effort. Astrometry isn't just some academic exercise. It's the absolute foundation of keeping our planet safe. At the very center of this global effort is the Minor Planet Center, or the MPC. This is the official international hub responsible for recording all this data. Millions of precision measurements from robotic telescopes all over the world are continuously funneled into the MPC every single day to constantly update our map of the solar system. Today, a lot of these robotic telescopes operate almost entirely automatically, detecting the moving objects, calculating positions, and sending the data straight off. But even though software does so much of the heavy lifting, human confirmation remains absolutely vital. Human eyes ensure the data is correct and verify anomalies that software might misinterpret. Because this entire pipeline forms the very backbone of our planetary defense. Without these incredibly precise measurements, predicting dangerous approaches will literally be impossible. I really want to leave you with this thought because it's just so cool. It is absolutely mind-blowing that by simply analyzing a few digital pixels on a sensor, running them through a database acting like facial recognition for the stars, and applying some heavy math, we can map the exact paths of massive, mountain-sized rocks millions of miles away in the dark. Through astrometry, we quite literally transform pixels into orbits. So we've cracked the code on tracking a newly discovered asteroid's journey to keep our planet safe. But that leaves us with one really big, lingering mystery. If we are literally just looking at a tiny, distant dot of light on a screen, how can we possibly measure its physical size? How do we know if it's the size of a car or the size of a massive, sprawling city? Well, that is exactly what we're going to explore in our next explainer. Thanks for hanging out with me today, and keep looking up.